Hello everyone. This time we will continue to work on project 5 of Nand2Tetris. Last time I have covered the implementation of the memory module. This time we will look into the CPU. CPU stands for Central Processor Unit. It is the center of a computer. What it does is data processing. Let's open up the chapter 5 of the textbook. You may find CPU here. Let's move on to the drawing in another window. Here, a CPU has 3 input ports. In M, which is the input from a data memory, and the instruction, it fetch instructions from the read-only memory. The read-only memory stores the instruction that tells CPU what to do. The reset pin brings the CPU and the entire computer back to a known starting point. The Alt-M is the output data to the data memory. Write-M is a single-bit signal tells the data memory to take a new input value. Address-M specifies in which memory location that the new input value the memory should put it in. And the PC is a program counter that point to one specific let's look at this diagram. PC point to a specific address location inside the read-only memory. Although it is called read-only memory, you can write data to it. It is read-only during the program execution. You can see there's no write to ROM signal, so you can only read from it. To get started, we have this drawing. This time, instead of using a hand drawing, I use this tool called diagrams.net. This is a very handy online tool. You can get access to your file anywhere, any computer. Okay, let's have a look. Inside CPU, the most important part is our ALU, implemented in previous video. It does arithmetic and logic operation. Also, we got 3 registers: data register, D register, address register, A register, and also the PC counter. In addition, we got 2 main muxes. And a decode unit. This is the most important part following the ALU. What it does is to decode the instruction and control other unit, control the function of other unit. Here we got some control signals, which is separated from the output of the decoder. Decoder. Okay. And the decoder also takes some current CPU state, like 0 and a negation, which is based on the output from ALU. We will analyze each of these unit shortly. So let's start from instruction decoding. In our hack CPU, we have two types of instructions. The A instruction and the C instruction, which is classified according to the leading bit. If this the 15th bit of the instruction is 0, so it is A instruction, which has 15 bits of memory address. Whenever you see a leading 0, you load the 15-bit address to the A register. And if you have the leading 1, it is a C instruction, which does computation. Here is a definition of each field inside this C instruction. Apart from the leading 1, the next 2 bits are not used. So let's look at this bit, the 12th bit of the C instruction, AM, animate AM. Maybe on the textbook it has another name. What does AM do is it decides which input it takes from. If the AM equals 0, the input signal to the ALU is just the value stored in the A register. Otherwise, if AM is 1, the input value to the Y port of the ALU is a value that read from the data memory. And put it into the ALU Y port instead of the A register value. Here we got C1 to C6, which control our ALU. In this table, it shows a function specified by the combinations of C1 to C6. Actually, C1 to C6 corresponding to the ZX, NX, ZY, NY, F, and NO of arithmetic logic unit. Following the COMP field, we got the DST, destination field. It has 3 bits, D1 to D3. For your convenience, I name it to DA, DD, and DM. What it do is whenever we have a active 1. For example, in this line, we have a DM to be 1, so the result is stored into memory location that is specified by the value inside the A register. Well, if there's a active 1 in DD bit is here, so the result value is stored in the D register. You can have any combination of those 3. After the destination field, we have the jump condition. Jump condition tells the CPU load the address address specified in A register to the program counter if any of those 3 value are examined. For example, if we have a GGT, which is a jump if greater than some value, the computation result is greater than actually it is greater than 0. So we jump to the replace the value already in PC with the new values that is stored in A register. And the PC tells CPU to fetch the next set of instruction from new location inside read-only memory. Yeah, that's what we have in our C instruction. So back to the drawing of our CPU. Okay, we need to follow those definitions to implement the decoder logic. Okay, I have labeled each signal inside this drawing, so it is easier to track which signal are connected to which component. So let's get started. Open up our what's this? Visual Studio Code. Can I maximize this? Let's start it by putting some important parts, the skeleton of our CPU. I would like to start from the ALU and registers, and then muxes. At the end, we have the decoder. For ALU, we only have one ALU, so it is easy. Here, use this template. We have the X signal, which is called Alt D. D register output a signal to the X port of the ALU. Alt D. Here we have Alt AM to the Y port of the ALU. You can name it what you want. And ZX, as I said before, the ZX are corresponding to the six comp bits inside the C instruction. So I would like to put CX is instruction 11, instruction, copy instructions over there. Okay. CX is 11th bit in our instruction. NX is 10th. CX is 9th. NY is 8th. F is 7th. And NO is 6th. So go back to our CPU drawing. What is the output from ALU? The output from our ALU is called Alt M, which is the output to the data memory. We also got a feedback signal to D register and A register, which is called Alt ALU. It's also connected to the output from or ALU. Okay, we also got a CPU state bits, ZR and NG. We call it ZR and NG by default. Okay, that's our ALU has been connected into our CPU logic network. Let's then do the registers. Let's do this A register. The A register is also an inbuilt part in Nand2Tetris. The input pin of the A register is called in A. The load signal to the A register is load A. We will implement the driving logic of load A later in this decoder implementation. The output from A register is called out A. Yes, that's it for A register. Next we got a D register. Similarly, we have a out ALU feedback from the ALU to the D register directly. Out ALU. Yeah. The load signal is load D, and the output signal is out D. Next, we have a PC program counter. We're not a template. Here, PC template here. The input signal to the PC is the output of the A register. That's out A. The load signal is load PC. The increment signal is INC. Okay, and the reset signal is the input port of our CPU, which just called reset. Let's copy it from here. The output signal from program counter is our PC, the lowercase PC. Please pay attention that the input signal to the PC and the internal register size of PC is 16 bits, and this lowercase PC only takes 15 bits, so we need to specify the zeros to 14s, that's 15 bits. Okay, that's it, our registers. Now, let's implement those two maxes. Max 1, and then another max. This max has an input A as out ALU. Just copy this. B is instruction. The selection signal is inst A. Meaningly, inst A specify if the instruction is A type, so it directly loads the value inside the instruction to the A register. The output from this max is called in A. Let's focus on this second max, A port is fed by Alt A, and the B port is fed by signal in M. Yeah, in M. That is the output from data memory to in M. The selection signal is called AM to ALU. Select from A register or memory and feed it to ALU. The output is Alt AM. That's it, our 2 maxes. Now it goes to the most complicated part, the decoder. Let's start from yeah, just to follow those part. So let's start from the ALU control, comp ALU. Comp ALU we have already done because we directly put instruction bits to the ALU instruction. Yes. So let's skip the ALU and start from inst A. Inst A logic. So let's see under what condition this A max selects instruction directly put it into A register. That's this case. If the instruction is A instruction like this, started by this at symbol. So to check if this bit is 0, so we need to do a negation first. Not instruction 15. Yeah, that's a 15th bit. If this is 1, so if this is 0, the negation of it is 1, because this inst A. Okay, that's our inst A logic. Whenever this instruction is A instruction, select the instruction and put it to A register. Otherwise, it is a C instruction, takes a feedback value from the ALU. Okay, the next would be D register. Follow this sequence. Load D. Load D. Under what condition the D register get loaded? Firstly, D register should be loaded if this instruction is a C type instruction. So and also the destination DD is set. So we would have a AND condition if both bits set. Instruction 15 and what bit is this? DD 5, 4, 3, so it's 4. The output is our load D. Load D signal. Okay, So next would be PC controlling signal. For PC, there are two signals. Inc is increment the PC. For example, PC is starting from 0. It takes a instruction that has a label value I. And then what it should supposed to do is to move to the next instruction. Increment the PC by 1 by fetching the next instruction one by one. So let's call it inc logic. Under what condition the PC should increment? It should increment all the way. So increment should be true. Let's do it on gate, which means put a true to the PC's increment port. Always increment without any condition. It should go to the next instruction on a arriving clock. Okay, after inc, let's do the load PC. So under what condition the PC should be loaded with values stored in A register? So let's look here. For example, here we got A register is preloaded with a label inside code memory, which is here, the memory address of this line. Load this to the A register, and here we got a jump C instruction. Jump is conditionless. It always jump. Always load the memory address of this line to the program counter. So the next clock, it will start from here to fetch the next piece of instruction. Load PC. So load PC is controlled by those jump conditions. We will start from simple conditions like jump greater than, jump equal, and jump less than, because they only get one single condition. Let's use this box to highlight them. Only one bit is set, so it's one hot. One hot coding. Those three conditions. Let's start from jump greater than condition. Under what condition should a jump greater than be active? Anyway, the jump is only exist in a C type instruction. So this should be loaded if is C. Yes, the C. We already got this one. if 15th bit is 0, so it's inst A. Let's copy this and reuse this signal. Let's put this inst A. And take the negation again. This should be the same value as the instruction bit 15. Let's call it inst C. So whenever this signal is 1, it indicates the current instruction is C instruction. Okay, let's look at jump greater than condition. So jump greater than, it means the 0 speed inside the C instruction is set to be 1 greater than, and also under a greater than condition, the current state of a computer should be greater than, should be a positive number. Let's first define what is a positive number. Positive output. A positive should be not 0 and also not negative. Not 0, not negative. So we should use neither. Neither means not. Not. Neither. Let's look up the truth table. Okay, it shouldn't be a Nand. It should be a yeah, neither. Neither. Is there a gate in not doing this. Neither. No. Let's look at this available gate list and see if there's a no, not. Yeah, that seems an NR is not provided in Nand2Tetris. So what we do is to have a all A, B, O, T. A is faded by ZR. B is faded by NG. And the odd is call it O. ZR, O, NG. What's that meaning? 0 or negative, that's contradiction. Anyway, call it state 1, and then take negation of this state 1, and put output as a positive pulse. Neither 0 nor negative, so that's positive. So let's continue work on our jump greater than condition. So it should be and instruction bit is G3, which is zeroth bit of the instruction is set, and also the current output is a positive number. Out is called GGT. Yeah. Okay, let's move on to the next jump condition. Will be JEQ. Jump if equal. So under what condition it is equal? Equal means the difference between two values is 0, so it will be 0 ZR. Let's do this, and A equals what's that bit? JE. J is the first, I mean bit number 1. The first is 0, so instruction, switch to English. Instruction 1. B input is a ZR condition of the CPU output. The out is JEQ. Jump equal. Next, we have this jump less than. Jump less than condition. Jump less than, so less than means a difference between of data to a reference number is negative, so you should take this NG. And which bit is G less than bit is the second, the number 2. So let's copy this. Number 2 and negative subtraction result, and GNG G less GLT. Okay, that's 3 one hot conditions. Let's do the combination of others. GE greater than or equal to. There's a GE is a combination of GGT and G equal. So let's do all. Sum of the product. GGT and B equals GEQ. Output is G greater than or equal to. Next we have a GNE, jump not equal to condition. Again, an all logic. GNE. NE is a combination of less than or greater than. GLT. Output is GNE not equal. And then we got GLE, jump if less than or equal to. use all. Was two combinations, GEQ and GLT. Output is GLE. Is this correct? Yeah. GEQ. Okay. What's next? Jump. Conditional-less jump. It always jump unless any. So it is combination of GLE and GT. GMP. Is G greater than or less or equal. That's a conditionless. It always means a condition. Yeah, we have implemented those seven jump conditions. 7 jump conditions. So any of those are satisfied. We do a jump, which is a load the A register value to program counter. So what we want to do is to have a nested OR structure to aggregate all those conditions. Is there an easier way? We will to aggregate 7 all conditions. We need 6 OR gates. Put the GT here, GEQ down here, and call this J1, GT, J1 is J2, J3, J4, J5, J6. Okay, I will put EQ less than, greater than here, not equal here, T less than here, and conditionalize jump here. And I put T2, T3, T4, and G5. Okay, let's see what is controlling the PC. It's a load PC. So we don't need a G6. We put a load PC. No. One more step. We need to identify if the current instruction is a C instruction. Then we do the jump. Otherwise, if it is a instruction, we do nothing. So should do a AND condition. And which one here? If it is a C instruction and there's any requirement of jump, then we set the load PC signal. Okay, that's it. Our loaded PC signal is quite complicated. PC. Next, we have to drive this the left max. It is easy. It is driven by inst A. Inst A, I think we already implemented. So just read a comment. On gate means we directly put our inst A signal to the gate. Yeah, it is here. Then we implement the driving, the selection signal of this the right max AM to ALU. AM to ALU logic. Let's see under what condition the memory content should be loaded to Y port and otherwise load the A register. It is controlled by this AM bit, remember? If the AM bit is set to 1, so it loads the memory content. AM is 1, yeah. So this one also on gate. Go back to AM to ALU. It is the 12th bit of the no. One more step. If this instruction is a C instruction, then we do this. Yeah, we need one more step, cannot directly on gate. And it is a C instruction. Also, the 12th bit is set. So we set the AM to ALU to select the memory content from data memory. Let's see what's next. Yeah, I think that's it. Wait a moment. Yeah, we still got load M signal. Load M signal which drives which tells data memory to take new value. So we need to implement this. Load M. This is simple. First let's copy this. First we need to check his C instruction and then load the data memory. And also check the destination field. The destination is data memory, so we set this bit. Data memory, so it's the 3rd bit. And load them. What else do we missing? Let's see, instruction. Yeah, it is handled here. In M is handled here. Reset. reset to the power to the program counter. Yes, handled. Alt M. Alt M. Oh, Alt M is provided here. So red M. Red M. Oh yeah. This signal should call the red ham. So let's create a new port. Alt equals red ham. Okay, that's put it there. Address M. Address M is provided by a register. Address M. How many bits is in address M? I remember that's 15, but the label is missing. Address M. Let's check out the input gate. It should call the RAM. RAM 16 key. Is that what's the set? Yeah. Look here. Address M is 15 bits, so we only take the 0.14 here. Also need to pay attention here is PC output is also 15 bits. PC output, yeah, that's it. Address M is read to M, yeah. Load M, read to M. Load M is our internal label. Address M, PC. Is PC handled? PC output, yes. So I think that's it. Let's test it out. Run the hardware simulator. Okay, load the test script for CPU. Fast. Let go. Oh, there's some error. Line 53. A1 and odd ALU. A1 is 1. 53. Oh yeah. Shouldn't be a max, should be max 16. 16. Oh, is that 16? Max 16. Yeah, that's a 16 bit. 16 bits max. Tracking. Okay. LAN 102. Specify the sub bus is not the bus range. Specify the sub bus is not in the bus range. 102 out 0 to 14. 102 here. 0 to 14 out. Oh yeah, should be here. Red ham. What is red ham? Oh, red ham is just a single bit. Okay, what I'm looking for 15 bits. Address ham should be address ham. address M is outputted from A register. That's all A register. Yeah, need a 0.14 as a address M. Memory to the data memory. Memory address to the data memory. One more. Line 105. Load A has no source. 105. Load A has no. So where's load A? Load A should be the load signal of A register. Didn't I include that? A register load A. Only appear once. Load A instead is here. Load D. Load D. Yeah. Load A is missing, so I need to implement the load A signal. What is load A? Load A is if it is A instruction, so load A, or the destination field bit DA specify, we put the result into register A, so that's a OR condition. How to interpret it? Let's first check is instruction A type instruction, or destination DA. So that's a no, because it's a test A. It should check as a last one more step and the condition, and this is a C type C instruction, and the DA is set. Instruction 5th bit. So that's a destination. Put the signal into to the A register. In C instruction, put the result into D register, or it is A register. Ignore what else. Put the operand value into the A register. Yeah, that's it. Load A. Yeah, let's try it again. Reset, run. Oh, it starts running. Yeah, great. My implementation is successfully done. Thanks for watching. Please thumb up and subscribe if you love my video.